Hello, ladies and gentlemen. Welcome back to online learning. Hope your spring break was fantastic. Today we are going to jump right back into topic 8. We are going to do one day of topic 8.4 where we are looking at real-world situations that can be modeled by quadratic functions. And I had you write in the concept summary on the left-hand side first. The concept summary tells us where there are two most practical uses for quadratic functions. The first one goes with our first example, so I'm going to talk about that first, is we use it for area. When the length and width of a rectangle are both unknowns, so they have their variable expressions in them, a quadratic function can be used to model the rectangle's area because we can use the double distributive property to multiply that out to get a quadratic function. So that's what the first example was talking about. In example 1, they said that there was a pool that had a length of 2x and a width of x, and they had this deck around it which was 4 feet on all sides. And so they wanted to find the area of the entire pool and deck combined and figure out if they had a length of a pool of a certain value, what was that area. So in order to do that, we have to notice that the length of this entire side is x, and then we have to add the deck to it on both sides. So x plus 4 plus 4. So it ends up being x plus 8. And then down here at the bottom is that same thing where we have the 2x, which is the length of the pool, but we have to add 4 to it from both sides. So 2x plus 8. Okay, so if we want to find the area of the pool and the deck, we want to multiply this side length by this side length, because remember, area is length times width. So we're going to do 2x plus 8 times x plus 8. Okay? We're going to use the double distributive property, so I'm going to multiply 2x times x and 2x times 8, and I get 2x squared plus 16x, and then I'm going to multiply 8 times x and 8 times 8, so plus 8x plus 64. Okay, and then I can combine these like terms. 16x plus 8x is 24x. Okay, so the area of this entire thing is 2x squared plus 24x plus 64. Now they told us in the problem that the length of the pool is actually 15 feet, so that x is going to equal 15 feet. So we can find the area by plugging it in to that function. So 2 times 15 squared, whoops, not to the 15th power, plus 24 times 15 plus 64. Okay, so when I do all of that math into my calculator, I end up with 874 feet squared. So the area of the entire pool is 874 feet squared if she has a pool that has a length of 15 feet. Okay, the second way that quadratic functions are used in real life is with vertical motion. So I talked a little bit about this I think when we were still in school, about like the arc if you throw a ball. And last week or 2 weeks ago, we did an example about a person shooting a soccer ball into a goal and the arc of that. This is the same thing as that. So a vertical motion model gives you the height in feet of an object t seconds after its launch. So in this example, they're talking about someone diving off of a high jump or a high dive. Okay, so this h sub 0 is the initial height. Sub 0 just means initial. Okay, so it's where the person or the thing starts from. And then this v sub 0 is the initial velocity. They will tell you what the initial velocity is because we won't figure that out. And then this negative 16 in front of the t squared, that actually comes from gravity. So the Earth's pull on that object while it is falling is that negative 16. So the height in feet of an object after t seconds is equal to negative 16 t squared plus the initial velocity times t plus the initial height. So in that second example, we had this person diving off of the high dive, and they told us that their initial velocity was 16. And by the picture of them diving, we could tell that their initial height was 30 feet. Okay, so we're going to plug that in to that vertical motion function. So h of t is negative 16 t squared plus the initial velocity times t plus the initial height. So negative 16 t squared plus 16 t plus 30. Because the initial height was 16, the initial velocity was 16 and the initial height was 30. Then they asked us to find this maximum height of the diver. Now, if I'm looking at the shape of the dive, that's a parabola. The maximum, remember, is finding the vertex. So if we're looking for the max height, that means the vertex. Remember, the vertex is found by negative b over 2a. Okay, so I'm going to plug in negative b, the b is 16, so negative 16 over 2 times my a, which is negative 16. That actually turns out to be 16 over 32, which is 1/2. So this is telling us that when he is at this maximum point, he's half of a foot away from the diving board, which is not very far. And then what it's going to tell us is when we plug 1/2 back into our function, we're going to get out the height that he is at. So I have to take this 1/2 and plug it in here. So h of 1/2 negative 16 1/2 squared plus 16 times 1/2 plus 30. So this ends up being negative 4 plus 8 plus 30, which is 34 feet. So he is at 34 feet at his maximum. Now, I think that the actual question was asking how far is he above the platform. So if he starts at 30, when he's at his maximum, he's actually 4 feet above the platform. Okay? So then I wanted you to do the try it on this one because it's just a little bit different. The try it said that they have an initial velocity of 8 and an initial height of 20. I want you guys to try this one on your own And then you can look at my picture of the notes when you're done to see if you got it right.